Lake Powell is vanishing, and not in the simple way most people imagine. Have you ever wondered what lies beneath when a reservoir dries? What secrets does Glen Canyon's bedrock hold once the water is gone? As of spring 2026, the answer is becoming clear. With the lake's surface plummeting, decades of hidden geology are resurfacing. Lone Rock, once a lone island in Powell's waters, now stands dry and connected to shore. What we are witnessing is not just a lake shrinking, but a landscape being reborn. In recent months, Lake Powell's water level has dropped to record lows. Bureau of Reclamation data in April 2026 put the lake's surface at about 3,528 feet above sea level, roughly 170 feet, approximately 52 meters, below the 3,700 foot, approximately 1,128 meter full pool mark. In other words, the reservoir holds barely 25% of its designed capacity, around 5.72 million acre-feet, or about 7.0 cubic kilometers of water. Forecasts for spring runoff are grim. Forecasters expect only about 2.3 million acre-feet, approximately 2.8 cubic kilometers of snowmelt to reach the lake by summer, about one-third of the historical average for this period. Snowpack across the Colorado River basin was astonishingly low this winter. Colorado recorded only about 40% of normal snow, and some headwater regions saw less than one-third of typical snow. In practical terms, the mountain water towers are nearly empty, and the river is acting like a water thief. Not surprisingly, experts say that reservoirs in the southwestern United States are holding just a fraction of their former volumes. One recent report notes that Powell and Lake Mead together have gone from years' worth of reserves to more than two-thirds empty, warning that another dry year could push them to the point of dead pool where even power generation and water deliveries cannot be sustained. On the ground, the change is nothing short of dramatic. Everywhere Lake Powell's water recedes, the exposed canyons tell a new story. At Lone Rock Canyon and along the upper Colorado, former shorelines have reappeared as sheer scarps of sand and mud. Beach terraces, 10 or more feet high, approximately 3 meters, now stand where waves once lapped, and vertical walls of layered sediment mark the lake's former edge. In satellite images and on hikes around Glen Canyon, one sees broad benches of pale clay, dried lake bed, and sharp banks carved where the water settled these layers. Photographers have captured strikingly pale bands of rock encircling the cliffs. These are the mineral and algal-stained lines of historic high water marks, layers of sediment laid down in previous decades of full reservoir. In short, every canyon wall has become a timeline. Technically, what this means is that the story of Lake Powell is now being read in its sediment and stone. Geologists note that since the dam was built in the 1960s, the reservoir has alternately flooded and exposed the Glen Canyon shoreline many times. When the lake rises, fine mud and silt settle out and coat the flooded beaches. When the lake drops, those now exposed beaches dry out, and river currents carve into them or lay down coarser sand and gravel. In geological terms, this produces an alternating stratigraphy along the shore, one layer of organic-rich mud, overlaid by one of coarser sand, then mud again, and so on. Scientists have described it like reading the pages of a book. When research sites were underwater, mud and other sediments were deposited by the lake. During times when the lake level was lower than the sites, the land was exposed to the air, and river channels brought in new sediments. Each rise and fall cycle over the past 60 years has left its mark. With the latest exposure, researchers can literally climb the beach ridges and measure these layers. This phenomenon is sometimes framed as Lake Powell acting like a toll booth for sediment. When rivers enter the still reservoir, they lose energy and drop their load. As hydrologist Casey Root notes, Lake Powell acts as a toll booth for rivers in the upper basin. As water from the rivers passes through the reservoir into the lower basin, sediment is left behind. Over years, the lake floor has accumulated thick piles of mud, silt and sand. Now that water is gone, the edges of those piles are visible along the new shoreline. In places, you can see fine grey lake mud capped by yellow river sand, literal pages in the canyon's sedimentary record. All of Glen Canyon's famous side canyons are emerging from their long slumber. In fact, between its various tributaries, roughly 100 river miles, approximately 160 kilometres, of channels have flowed again, and hundreds of acres, tens to hundreds of hectares, of new land lie exposed above the current waterline. Think of it as though decades of underwater washes and alcoves have been unearthed. In Lone Rock Canyon itself, climbable canyon walls that had been permanently submerged are now walked on dry ground. Narrow side canyons and alcoves, which visitors used to pass by boat, can now be explored on foot. Many of these passages were originally carved by the Colorado River or its tributaries long before the dam, and they persist as striking slot canyon walls and overhangs. When full, Lake Powell hid them. Now they are back in daylight, showing how water relentlessly etched and undercut the Navajo and Kayenta sandstone over time. How did those dramatic slot canyons and caves form in the first place? The answer lies in episodic erosion. The region's rocks, especially the Jurassic Age Navajo sandstone that dominates the canyon walls, were laid down as giant desert dunes about 190 million years ago. Tectonic uplift in the last 5 to 6 million years raised these layers high above sea level, and then the Colorado River began cutting through them. The result is Glen Canyon's vast, twisting channels. In normal times, small side streams carry only moderate flow, but during rare, intense storms, they can unleash violent flash floods. Geologists call the narrow canyons slot canyons because floodwaters concentrate and blast through the bedrock. These floods can scour sand, rock and debris, carving the sinuous, polished walls that slot canyons are known for. What is new at Powell is that many of these slot channels have been inactive for decades or longer underwater, and are now active again. As rains fall on the exposed sandstone, that water rushes down old channels, deepening and widening them once more. Researchers have even observed fresh sediment being gouged out of re-exposed stream beds within weeks of storms, a vivid reminder that the erosive power of even a few cubic meters of water can be immense when it funnels through a canyon. Meanwhile, the sheer cliff faces themselves are telling a story. When Powell was deep, wave action lapped against the limestone and sandstone ledges, smoothing some and undercutting others. Those underwater abrasion processes often leave behind small caves or grottos along the shore. Now, as waves retreat, these features stand out like amphitheatre niches. Some are true caves, a few meters deep, carved at former shore heights by decades of gentle wave erosion. Others are overhangs, where resistant rock layers form a cap and softer layers below have been eroded away. In a few places you can even see a dried waterfall basin or sluiceway, where water once cascaded out of a sidewash. In short, the landscape in Glen Canyon is three-dimensional geologic art, with cliffs, benches, alcoves and arches all suddenly accessible. Yet these newly exposed shores are hardly static scenes. Physical weathering has started immediately. With the lake bed dry and exposed to air and sun, cracks in the rock layers begin to form. Overnight temperature swings, and the occasional rain can break apart the mud layers, causing small mudslides or boggy patches. In fact, some of the old lake sediments act almost like quicksand. The finest mud can stay so waterlogged that it liquefies underfoot. Walking out there is not easy. Fine dust rises in the breeze, and invasive desert plants like tumbleweed are already colonizing the sand, their root systems prying the sediment apart. where films of microbial mats or algae stain the old shoreline. Sunlight now darkens those patches, marking the interface between water and land. All of this is raw geological process, the re-oxidation of minerals, the mechanical breakup of old deposits, and the re-initiation of desert erosion now that moisture is absent. At Bullfrog, the problem is not simply that the lake is low. The real problem is that the shoreline has moved faster than the marina can sit still. A floating marina only works when the water beneath it remains deep enough, stable enough, and predictable enough to carry boats, docks, fuel, and service craft without grounding them on sediment. The National Park Service was already warning that changing water levels were creating new hazards and forcing marinas to reposition. In that setting, the temporary move of Bullfrog Marina to deeper water near Hall's Crossing is not just an operating tweak. It is a direct response to a shifting geologic boundary. That matters because Bullfrog is not being relocated into a vacuum. The move is happening in late April and continuing through mid-May, in phases with the marina, boat rentals and fuel dock shifted toward the main channel where the water is more reliable. Land-based services at Bullfrog stay open, but the floating piece of the operation has to go where draft still exists. The reason is plain. Shallow water is no longer an inconvenience there, it is a structural limit. When the lake surface drops below the operating envelope of a launch area, docks lose clearance, gangways become awkward or unsafe, and the bottom starts competing with the hull. The geology at Bullfrog makes that drawdown especially disruptive. Marina sites in reservoirs are built on a moving interface between water and sediment, not on a fixed bedrock floor. Every time a river enters still water, it loses energy and drops sediment. Over time, that sediment builds deltas, submerged benches, and soft shoreline aprons. The United States Geological Survey has described Lake Powell as a place where mud and other sediments are laid down when sites are underwater, and where lower lake levels expose land to air and let river channels bring in new material again. That cycle is now visible at Bullfrog as the lake edge steps across former deposits instead of stopping at one line. That is the key to understanding why Bullfrog is harder to keep in place than a casual observer might think. A marina can tolerate low water for a while if the bottom is firm and the slope drops away quickly. But if the shoreline sits on a sediment apron made of fine lake mud, sand, and reworked delta material, even a modest drop in elevation can translate into a large horizontal retreat. The lake does not merely go down, it pulls the shoreline outward, exposing more soft ground, more shallow bars, and more places where a floating dock can lose support. The move to Hall's Crossing is therefore best read as a search for deeper, more stable water in the main channel rather than a simple change of address. That sediment behaves in ways that matter for infrastructure. Fine reservoir mud dries into hard crusts on the surface but can remain weak below, especially where water still lingers in the pore spaces. Underfoot it can feel solid until weight is applied, then fail suddenly. That is a soil mechanics problem, but it is also a geomorphic one. Once the water retreats, the old reservoir floor begins to compact, crack, slump, and shed loose material into lower spots. Around Bullfrog, that means the active margin is not a clean line on a chart. It is a broad transition zone of changing grain size, changing moisture, and changing stability. The National Park Service's recent guidance makes the operational consequences explicit. It warns that changing water levels narrow channels, shift hazards, and alter the usefulness of floating walkways, fuel docks, and pump-out stations. It also says that repositioning marinas is part of how the park is keeping access open as water levels keep moving. That is a strong signal that Bullfrog's relocation is not an isolated maintenance project. It is part of a larger shoreline adjustment driven by a lake that is shrinking in elevation while simultaneously reworking its own margins. Hall's Crossing is the logical temporary destination because it offers deeper water in the main channel, which is less vulnerable to immediate grounding than the inside of a shallow bay. The relocation report says the move is aimed at a more reliable water depth, and the park's marina page places Hall's Crossing directly across the lake from Bullfrog. That arrangement matters geologically because the main channel tends to retain depth longer than the margins of an embayment, where sediment accumulates more easily and the bottom rises faster relative to the falling water surface. The marina is effectively following the deepest usable trough left in the reservoir. The contrast between the old and new positions is not just about water depth, it is about shoreline shape. Bullfrog Bay sits in a part of the reservoir where the lake has enough room to spread out laterally. That geometry encourages the formation of gentle underwater slopes and broad sediment flats. When water recedes from such a setting, the shoreline migrates a long distance for every foot of elevation lost. That is why one can move from waterfront to dry ground surprisingly quickly at Bullfrog. The same vertical drop that looks small on paper can expose a wide swath of lakebed in plan view. Once exposed, those margins are not passive. Wind begins to move fine sand and silt. Sunlight and heat dry the upper layers, causing shrinkage cracks. Occasional runoff from storms can then cut through the weakest parts of the exposed sediment, carving small channels that feed into larger gullies. In a reservoir setting, those gullies do not need to be large to matter. They can undermine local access roads, erode ramp approaches, and make it harder to move heavy marina gear. What looks like a temporary docking inconvenience is therefore tied to the same erosional physics that shapes badlands, deltas, and dry lake margins everywhere. That is why the temporary move is being done in phases. Floating docks are not simply packed up and driven away. They have to be repositioned where the water remains deep enough for safe towing and reassembly. Some boats can move with the docks, while others may need to be towed separately depending on depth and local conditions. The relocation report also says a shoreline access route and walkway are being prepared near Hall's Crossing, with water taxi options under consideration. Those details reveal the physical reality behind the headlines. The marina is not just changing location, it is being rethreaded through a lake edge that is still actively changing shape. This is also why the permanent future matters. The National Park Service says a long-term ramp at Stanton Creek is being planned as a lower elevation solution, though it will not be ready for the summer 2026 season. That project is important because it acknowledges that the old shoreline geometry at Bullfrog is no longer a reliable foundation. A ramp designed for lower lake elevations is, in effect, a geologic adaptation. It assumes that the reservoir margin will keep migrating and that infrastructure has to live with that migration rather than pretend it is temporary. Bullfrog Marina also sits inside a broader pattern that the park has been documenting for years. The park's changing water guidance says that since 2001, declining water levels have reshaped Lake Powell's shoreline, affecting launch ramps on lake facilities and navigation. That larger trend is what gives the Bullfrog move its meaning. The relocation is not a one-off response to one bad season. It is a practical acknowledgement that the lake's edge is now a moving target, and that the edge itself is being rewritten by sedimentation, erosion, and drawdown together. For scientists, Bullfrog is useful because it compresses a big process into a visible event. Reservoir drawdown is often discussed as a water supply issue, but Bullfrog shows how directly it becomes a landform issue. When a marina must migrate, the lesson is not only that the lake is low, it is that the reservoir floor has become part of the terrestrial environment again, with all the instability that comes with drying, cracking and reworking unconsolidated sediment. The shoreline is no longer a fixed boundary between land and water, it is a wide, active transition zone where both are trying to reclaim the space. The deeper story is that Bullfrog is being asked to operate in a basin that is losing storage faster than it can absorb change. Reclamation's recent reports describe Lake Powell under severe hydrologic stress, with low snowpack and inflow forecasts that keep the system under pressure. When inflow weakens, the lake does not merely lower by a fixed amount, it loses the buffer that smooths out seasonal swings, which means shoreline facilities feel each change more sharply. In that sense, Bullfrog is the front edge of the lake's response to drought, one of the first places where the changing balance becomes visible in concrete, steel, dock floats and access routes. Lake Powell, in a nutshell, is this: a canyon reservoir that stores water by flooding a landscape built of rock and sediment, then gives those materials back whenever the water falls far enough. Bullfrog Marina is one of the clearest proof points. It sits on a shoreline that can no longer be trusted to stay put, so the marina is moving to where the lake is still deep enough to work. That is the entire system in miniature: water rising, water falling, sediment settling, sediment drying, infrastructure adapting, and the reservoir proving that it is not a lake in the normal sense at all, but a temporary skin stretched over a geologic surface that never stopped changing.